Hello and welcome to my talk about scaling up set similarity joins using a cost-based distributed parallel framework. This is the agenda. First, I would like to introduce set similarity joins and the problem statement. I want to talk about existing approaches and the motivation for our new approach. Next, I would like to introduce our distributed approach, present experimental results, and conclude. What is a set similarity join used for? It can be used for plagiarism detection. So if you think of documents which contain parts of other documents, we could find such similar passages in different documents. We could use it for deduplication. So when whole documents are identical or close to identical, we can find such pairs and eliminate the duplicates. We could also use it for fuzzy joins. So when you think about two tables which do not have a join key, but other, for example, textual attributes that match in a fuzzy way, we could use the set similarity join to find matching rows in two tables. This is the definition. The input is a collection of records R, where each record consists of a set of tokens. We need a similarity function, which gives us for each pair xy of records a value between 0 and 1. 0 means both records are not similar at all, and 1 means they are the same. And we need a similarity threshold theta. We can choose this between 0 and 1. The output are all pairs of records where the similarity is above this threshold. This is the problem statement. How can the set similarity join be efficiently computed? By efficiently, I refer to scalability and robustness, especially when it comes to different data characteristics. On a potentially large input dataset, by large input dataset I mean several hundreds of gigabytes, and I focus on textual data here. Textual data means I assume a Zipfian distribution and usually very high counts of different tokens. Given a large number of shared nothing nodes of modern commodity hardware. So I think today it is realistic to assume that we have hundreds or even thousands of compute nodes available for just one operation, which is realistic when you think of cloud computing. Furthermore, modern computers usually have multi-core CPUs, and we also want to use this parallelization potential here. The naive approach to compute the set similarity join is to create the cross product and then to compare each pair individually, and as you all know, this is not very efficient, so already for very small data sets this doesn't work. This is why the filter and verification approach emerged. It uses so-called filters to ignore hopeless pairs. So these yellow bubbles here on the left side, they are our input records, and filters generate candidate pairs. These candidate pairs are a superset of the result pair, so we do not lose anything with this filter technique. And the hope is that these candidate pairs are a lot less than the cross product would be. In the second step, the verification, each of these candidate pairs is verified with the similarity function and checked against the similarity threshold. One important note here is the complexity of filter and verification is still quadratic in the worst case, but in practice we have much fewer comparisons than with the cross product. So here are some basic filters that are important. The most important one is the length filter. I will also use this one throughout this talk. So only records within a certain length range may be similar. So when we have two records and they also have a similar length, like you can see here, so these two records would survive the length filter and these two records would not survive a length filter, of course given a certain similarity measure and a certain similarity threshold which are omitted here. There's also a prefix filter, for example. Two records may only be similar if their prefixes share at least one token. So these two records here have a prefix. This is the left part here, and it is sufficient to only look at this left part in order to find out if they can potentially be similar. They are potentially similar if they share at least one common token here. If they do not, like in this example down here, they cannot be similar. A basic algorithm that uses both of these filters is called all pairs, which is also the basis for our approach here. All previous algorithms we looked at use inverted indexes for candidate generation. I just wanted to mention this word here because it is a crucial construct we use, and you will hear it later. So this is an overview on filter and verification approaches so far and where our new approach comes in. So first, single core algorithms came up, and there's an experimental study on many of these, or up to that time all of them, from Mann et al. In VLDB 2016. Then, based on the assumption that dataset sizes increase, many MapReduce-based approaches emerged, and we compared these in a VLDB paper in 2018. Last year I presented an adaptation of the filter and verification approach to multi-core CPUs. And this is where the new work comes in. So I use the multi-core version of the filter and verification approach and add distribution, or make a distributed framework on top of it. Why do we need a new distributed approach? I mean, we already have the MapReduce approaches, right? So our experiments in the previous papers showed that the maximum input data size these MapReduce algorithms can operate on is quite limited. So in our setup it was roughly 12.5 gigabytes. Interestingly, our multi-core approach, which runs only on one machine, of course, could operate on up to 25 gigabytes. So these numbers are still not very impressive when you think about big data. So it's a challenge to push these input dataset sizes. Based on the results from the MapReduce algorithms, intranode data replication is inefficient. MapReduce algorithms often do it, or maybe have to do it because of the programming paradigm, and we avoid this here. Recomputation is also inefficient. By recomputation, I mean repeated validation, for example, of a candidate pair, and also algorithmic data dependencies can be dangerous. So, for example, in the MapReduce case, we see this utilization graph here. So on the y-axis we see the number of tasks, and on the x-axis we see time. And at first the utilization is quite good, and then the utilization decreases, and we have a long tail here of straggling reducers. So this is due to skew, which occurs because the algorithm is dependent on certain data characteristics which were not good in this case, and we found that it is actually most algorithms suffer from this problem so far. We develop an optimizer to tackle these last two problems. Our assumptions are as follows. We abstract from a specific distributed system, so our approach could potentially be implemented in many distributed systems so far, and we assume a large number of compute nodes, as I said before. This is the data flow. We start with the input data, the raw objects, which are texts in our case, and we tokenize them to integer, we clean them, and we count their statistics. So the tokenization, that's already the case for all previous set similarity join algorithms. The length statistics are new in our case. The length statistic is a list where we have all occurring lengths in the input data and the respective record counts to it. Starting from these length statistics, we run our optimizer. The optimizer is an offline optimizer which creates execution parameters. So these execution parameters together with the tokenized data are the input for the distributed similarity join, which produces the end results, the object pairs. The distributed similarity join is composed of many machines. So each white plane here is one node, and on each machine we run the multicore SSJ locally. We assume that each node already has access to the whole input data set. So either it's already copied to its hard disk or it's available via a distributed file system. And the machine also gets its dedicated set of execution parameters which we computed before. This is the core of our optimizer. It's a cost-based heuristic to distribute the computation costs as evenly as possible. So the basic idea of it is the length filter. This is a join matrix here based on the lengths of the records. So in order to get a full result, we need to join all the lengths, like in this case length 1 and length 1, length 2, length 2, length 2 with length 2 and 3, and so on and so forth, in order to get this full result. Note that each square in this join matrix could potentially be computed independently. However, we group them together in so-called slices, and we define that the y-axis here are index lengths and the x-axis here are probe lengths. So each index length composes one slice. Each of these slices can be computed independently. Next, we estimate the compute costs per slice using the length statistics. I omit the formula here, it's in the paper. Let's assume these costs here to the right, which are the respective costs to each slice. Then we assign slices to n groups. We predefine n such that the costs are distributed evenly with a greedy heuristic. Let's have a look at an example. If we choose n equals 2, we get 2 groups. Then we sort the slices, for example, by descending order of the costs. So the first slice we get then is slice 2, and we assign it to group 1. The next slice would be slice 3 with the cost 3, which we assign to group 2. The next slice would be slice 1, which we assign again to group 1, and so on and so forth. And in the end we get costs of 6 for group 1 and costs of 5 for group 2. Another important mechanism for the optimizer is the data-independent scaling. We use the modulo function to further partition slices into sub-slices. So let's look at the example from the previous slide again with an additional scaling parameter m equals 2. So each square which was in here before we divide by m, so in this case it's 2, and we get these subsequent sub-slices. So group 1 actually has group 1 orange here and group 1 blue, and group 2 is also divided in the same fashion. An important property here is that we distribute the record lengths evenly amongst these sub-slices. Another important part of the optimizer is the RAM demand estimation. The RAM demand estimation needs already existing parameter values for m and n, and its aim is to avoid the worst case, which is swapping. This example motivates why this is so important. This is one data set we used. We enlarged it by the factor 100. This is the similarity threshold here, and these are the parameters. When we choose m equals 64 and n equals 8, this means we use in total 512 nodes. We get a runtime of more than 12 hours. When we use the same amount of nodes with a different parameter setting here, which is m16 and n32, then this only takes 200 seconds. And the reason for this is indeed swapping. So we estimate the RAM demand for our implementation of the set similarity join based on the index size and the probe records. Both of them we can estimate exactly beforehand. The candidates are unknown a priori, so we can only estimate them very roughly. And there's other static overhead, for example, program variables and things like that. Everything together must stay below the system RAM, which is available on all our nodes. So when we go back to this example here, our RAM demand estimation estimates 37 gigabytes here in the first case, which is larger than the system's RAM, and it would assume 24 gigabytes for the second one, which is below it, and indeed no swapping occurs. So our estimation worked in this particular case. There are further details of the optimizer. I only briefly go into them here. We also evaluate the quality of the cost distribution. So in this graph here, in the right one here, we can see these bubbles. Each bubble with the same color marks that they have the same number of nodes. For example, so this one here has 60 nodes, this one has 60 nodes, and the size of the bubble marks how long the execution took. So you can see this is quite similar here, so it doesn't matter which of these two combinations of parameters we use. However, here to the left graph we see that this can make quite a difference. So in this case, this combination of parameters would be beneficial for the runtime. So we make sure that we use a good parameter combination regarding the runtime. We also discuss a parameter finding strategy on how to find good values. So this is one experimental result. Let's start with the cost-based heuristic. We only vary the parameter n for this. So this is a graph for one example data set. On the y-axis, there is the time, the runtime, over all slices, the maximum runtime over all slices. So this is the runtime that dominates the overall runtime. And on the x-axis, we see the parameter n. The different colors of the lines mark different similarity thresholds. So for a low similarity threshold, we get, of course, very large runtimes. For a lower one, for a higher threshold, we get very low runtimes. And so, as you can see, the runtimes go down quite a bit with an increasing n. However, there is a certain n where from which it is not beneficial anymore to increase it even further. There are some limitations which are by design. So the cost-based heuristic does not take length skew into account. So if our input data set would, for example, in an extreme case only have one length, then of course this heuristic wouldn't work anymore. And it also does not take into account candidate skew. So if you think of one slice having a lot more candidates than the other one, it needs more time to verify them, for example. So our heuristic could be too optimistic in this case. Another result about the scaling mechanism, so when we vary the parameter m, again, we have a graph here for one example data set. This is the maximum runtime over all slices on the y-axis and the m parameter on the x-axis. You can see that the runtimes decrease, and so the important property of the scaling mechanism is that the runtimes of all combinations of algorithms and thresholds decrease for increasing m values. Also the ones which were limited by length or candidate skew in the heuristic before. This can be expected because this parameter simply partitions the probe records within each slice. Increasing m has a positive value, runtime effect, except for very small data sets or very high thresholds, or if the runtime is already very low, because then we start measuring the static overhead. These are the conclusions. We presented a novel distributed parallel set similarity join. It only requires an additional length statistic. The optimizer avoids recomputation and distributes the compute load. The approach avoids skew and swapping, and it is highly scalable to hundreds of gigabytes of input data, as we showed in our experiments. However, candidate skew remains challenging because we do not know the candidates a priori. So for future work, it would be interesting maybe to integrate also GPUs in this approach, and maybe to use machine learning or other techniques for candidate estimation, and to adapt it to an actual big data system. Thank you.